Good day everyone. Today we will discuss on the first part of the two-dimensional motion, which will focus on the projectile motion. But first, let's look at the difference between the motion in one dimension and two dimensions. In the previous topic, we discussed about one-dimensional motion, which can be described as either motion along x-axis only or along y-axis only. So the two-dimensional motion, on the other hand, is a combination of the motion along x and y axis. In other words, motion in two dimensions is the motion along xy plane. So the most common or the simplest examples of 2D motion are the projectile motion, which is a 2D motion along the vertical xy plane, and the uniform circular motion, which is usually along a horizontal xy plane. And we will discuss more about uniform circular motion later, but as of now, we will focus first on the projectile motion. Since 2D motion is a combination of motions along two axes, the objects moving in 2D has two sets of quantities, which we call these the components. The x component, and we also have the y component. So given that, we also have two sets of quantities to work with. So we have two displacements, the displacement along the x-axis and the displacement along the y-axis, just like how we separate the x and the y components of a vector. And we have x and y components for the velocity as well as x and y components of the acceleration. Since we have two sets of quantities, we also have two sets of kinematics equations to deal with in 2D motion. So here we have kinematics equations for the x component and another set of kinematics equations for the y component. Now, when can we say that a motion is a projectile motion? So, by definition, an object moving in a projectile motion is called a projectile. And a projectile is any body that is given an initial velocity and then follows a path determined entirely by the effects of the gravitational acceleration. So hence we have two requirements for a projectile motion. Again, the first requirement is that it must have an initial velocity, and second, it must be under the influence of the gravity. And the path followed by the projectile, this path here, traced by the broken arrow, is called the trajectory. So the trajectory is dependent only on the initial velocity and its angle of projection and on the acceleration due to gravity. And here are some examples of the projectile motion for your reference. So in ideal situations, the air resistance is not taken into account for projectile motion. So in such cases, we can analyze the projectile motion as a combination of a horizontal motion with constant velocity and a vertical motion with constant acceleration due to gravity. So we have here a demonstration of the relationship between the free fall and projectile motion. The red ball is released directly downwards, hence free-falling object, while the yellow ball, on the other hand, is given an initial horizontal velocity, hence it is a projectile. So the figure shows a series of images taken at the same time during the motion of these two objects. Here we can notice that although the yellow have a horizontal um, a horizontal initial velocity, both of them reach the ground at the same time. So the reason for this is that the horizontal and the vertical components of motion are independent of one another. Also, the time of flight, or the time it takes for the objects to reach the ground, also known as the air time, is only dependent on the height at which these balls are initially positioned. Hence, since both of them are released at exactly the same height, they will reach the ground at exactly the same time. The only difference is that the yellow ball, which has a horizontal initial velocity, will land at a certain distance called a range, away from its initial position along the x-axis. So therefore, there are important characteristics of projectile motion that we have to remember. So first, only the y component of the motion dictates the time of flight. And second, only the x component of the motion dictates the range of the projectile. So because of this, we can therefore express all the vector relationships of for projectile positions, velocity, acceleration, by separate equations for the horizontal and the vertical components. So we go back to the general kinematics equations for the 2D motion and figure out what would these equations look like if we use them in projectile motion. So we have here the x component, the general x component of the kinematics equations for 2D motion, and as well as the general x component kinematics equations for the 2D motion. So, and we should take note of the characteristics of the projectile motion, like the y component of acceleration. A sub y is just equal to the acceleration due to gravity. This acceleration here, this one, and that one, that must be equal to the acceleration due to gravity. And then the x component of the acceleration is equal to 0, which means that this acceleration, and this one must be equal to 0. So immediately we will replace the acceleration in the y component by g, which is the acceleration due to gravity. Thus, the kinematics equation for the vertical component or the y component of the projectile motion is given by this set of equations here. And of course, without forgetting that g here is equal to negative 9.8 meters per second squared, which is the acceleration due to gravity. But how about the x component? So here I just written it as is, but let's examine what will happen to these equations one by one. So in the x component of the projectile motion, we have to take note that the acceleration is always 0, provided that air resistance is negligible. And because the acceleration is 0, the horizontal velocity must be constant throughout the motion. In other words, the horizontal component of the velocity must not change, or the initial horizontal velocity and the final horizontal velocity must be equal. So let us look at the equations to prove this. So here in the left, we have the general kinematics equations for the x component of two-dimensional motion. And what will happen to these equations if we implement these conditions for the projectile motion? So first, the first equation, this one, of course, the projectile motion says that its x component of the acceleration must be equal to 0, which means that this term here must be equal to 0. So what will happen is that this equation will be reduced to this. So this is 0, and so this will give us final the final horizontal velocity is just equal to the initial horizontal velocity. So this will reduce to this. Next, the second equation, again, this is equal to 0. So we are left with this equation. So that will give us x minus x sub 0, or x naught, is equal to the initial velocity, horizontal velocity, times the t, which means that the distance traveled along the x, or along the x component, is just equal to the initial x velocity times the time it takes for the projectile to hit the ground. The third equation, again, acceleration is equal to 0. And so we are left with final x velocity squared is just equal to the initial x velocity squared, which will also reduce to this. So this equation is just equal to this. And then lastly, we have the fourth equation. So take note that in our first and third equation, we know already that the final x velocity is just equal to the initial x velocity, which means that these two here are just equal. So if we add this and this, we will get 2 times the initial velocity, or we can also say 2 times the final velocity, because again, the final velocity is just equal to the initial velocity. So this one and this one are just equal, or we can represent them as the initial velocity, or we can also say that this is equal to the final velocity. So we will be given this 2 times the initial velocity, x velocity, divided by 2 times t, which will give us the initial velocity, horizontal velocity, times the time, which is also equal to this. So our first and third equations reduce to this, while our second and fourth equations reduces to this equation. So the kinematics equations for, therefore, the horizontal component or the x component of the of the projectile motion can be described by 2 equations only, as you can see here. So the kinematics equations for the x component of the projectile motion is that, first, this equation tells us that the final and the initial horizontal velocities are just the same, or in other words, the horizontal velocity of the projectile motion is constant. And second, the final position along the x-axis is equal to the initial position along the x-axis plus the initial horizontal velocity times the time. So the vertical component, or the y component of on the other hand, will just remain as is, since we already taken into account the constant acceleration due to gravity, which is equal to negative 9.8 meters per second squared. In other words, to summarize, the kinematics equations for the projectile motion, we have here 2 sets of equations, one for the x component and the other one is for the y component. So for the x component, we only have 2 equations, which are this, and for the y component, we have a total of 4 equations. So again, in projectile motion, the horizontal velocity does not change at any point in the trajectory. Hence, the x component of the acceleration is equal to 0. The vertical velocity, on the other hand, is changing, identical to that of a free falling body, because it has a constant acceleration of equal to the acceleration due to gravity. So to learn more about the quantities that describe the projectile motion, let us have here an illustration. This is how a typical projectile motion looks like. And if we show now the quantities and how they change throughout the motion and on each of these points in time, we will see something like this. So first, we must learn about the components of the initial velocity. So for projectile motion, we generally have x component and y component of the initial velocity. This is because most of the projectile are projected or thrown at some angle of projection indicated by this Greek letter alpha, sometimes alpha sub 0 or alpha naught, but sometimes angle of projection is also labeled as theta. So do not be confused of that. And just like in our discussion on vectors, we can calculate for the x and the y components of the initial velocity separately. So the x component of the initial velocity is calculated by multiplying the magnitude of the initial velocity by the cosine of the angle of projection. And the y component, on the other hand, can be calculated by multiplying the magnitude of the initial velocity by the sine of the angle of projection, as shown in these equations. Now, if it's the other way around, say for example, you have the values you are given the values of the x component and the y component of the initial velocity, and then you are asked to calculate for the magnitude of the initial velocity, all you have to do is to use the Pythagorean theorem. So the magnitude of the initial velocity is just the square root of the sum of the squares of the x component and the square of the y component, as shown in this slide, this one. Now, how about the velocity at any given time during the motion? So we usually refer to this as the final velocity. And in this slide, you can see that the x component of the final velocity is easier to calculate compared to the y component of the final velocity. When calculating for the x component of the x component of the final velocity, all we have to remember is that it is just equal to the x component of the initial velocity, for the reason that the acceleration along the x is equal to 0. So therefore, your final x velocity is just equal to the initial x velocity, and you can always calculate that um, taking by dividing the total x distance traveled by the projectile by the time interval. So, however, for the y component, the final y component of the final velocity, we have an equation here given by initial velocity plus the acceleration due to gravity times the time. So this equation is of course taken from the kinematics equation. So this is the difference of calculating the final velocity of the projectile. So the x component is easier to calculate because it is just equal to the initial x component of the velocity, which is equal to the distance traveled divided by the time. While for the y component of your final velocity, you still have to calculate for it using the kinematics equation, because as you can notice, we will add here the initial velocity or initial um, y component of the velocity plus the acceleration times the time of flight of the projectile. And to calculate for the total magnitude of the final velocity, all we have to do it again is to use the Pythagorean theorem. So the magnitude of the final velocity is just equal to the square root of the sum of the square of the x component and the square of the y component. So I hope you have mastered already calculating for the x component and the y component of the initial velocity, uh, v naught, and the final velocity, v. So there is an interesting point during the projectile motion wherein the y component of the velocity will equal to 0. So this point here is called the zenith, and this is the position where which is the highest point of the projectile's trajectory. So while the projectile is still moving upwards, the y component of the velocity decreases because of the negative acceleration due to gravity, as you can see here. So here you have a longer y component, and as you go up of the trajectory, you can notice that this y component of the velocity decreases in length, which means that the y component is decreasing, and that is because your acceleration is going downwards. Now, while the projectile is going upwards, the y component of the velocity decreases because of the negative acceleration. Then when the velocity and acceleration are antiparallel, you know that the object will slow down, hence the y component will eventually reach a value of 0 here at the zenith because of the deceleration caused by the gravity. So after reaching the zenith, the projectile or the object then begin to exhibit negative velocity, hence the object is now going downwards, as you can see here. Okay, so here your y velocity is still going upwards, but it is decreasing until it reaches the value of 0. And then after the zenith, you can notice now that the y component of your velocity is going down, and that is because of the acceleration due to gravity. So at the top of the trajectory, which is called the zenith, the y component of the velocity is 0, and after this moment, the velocity starts to have a negative value, indicated by the downward motion because of the influence of the gravity, as shown here in this arrow. Please take note. The x component of the velocity, on the other hand, remains the same because it is not affected by the acceleration due to gravity. Remember here that we are taking the x component and the y component independently. So the acceleration due to gravity is only affecting the y component and not affecting the velocity, the x component of the velocity. So the height of the projectile can also be calculated using the kinematics equation. So here, the height is just the final y position minus the initial y position. And at the zenith, which is the maximum height of the projectile, the the y component of the velocity is just equal to 0. Hence, this one here is just equal to 0 at the zenith. So um, the maximum height can therefore be calculated as the negative of the square of the initial y component of the velocity divided by 2 times the acceleration due to gravity. And remember that the acceleration due to gravity is negative 9.8 meters per second squared. So do not be worried when solving for the maximum height, which is the height of this zenith, because this negative sign here will eventually be cancelled out by the negative sign of the acceleration due to gravity. So you will definitely get here a positive value for the maximum height. So we can also solve for the range of the projectile. So this is the horizontal distance traveled by the projectile with respect to its initial position. So the range is referred to as this distance here. So the height is how high above from the initial position the projectile is located at given time. So the height is this one or that one or that one, while the range is referring to this position, this this or that one, depending what time interval you are referring to. So the range can simply be calculated using the horizontal kinematics equation for the projectile motion, which is this equation. So the range is just equal to the x component of the initial velocity times the time of the flight of the projectile, or the time it takes for the projectile to hit the ground. So the same equation can also be used to calculate for the horizontal distance traveled by the projectile at any given time during the motion, since the horizontal velocity here is constant. Say for example, you wanted to calculate the distance of traveled by the ball from this point of the projectile towards that. So you wanted to calculate this length here from this to this. So all you have to do is to use this equation where the range, which is equal to the final x position minus the initial x position, is just equal to the x component of your initial velocity times the time it takes for the ball to reach this position from release. So now let's talk about more about the angle of projection, because the components of the initial velocity, both the x and the y components, are highly dependent on this angle of projection. So keep in mind that just like the reference angle in our topic on the vectors, we measure the angle of projection from the positive x-axis towards the initial velocity vector as shown here. So this is how we measure the angle of projection. So we have here to look at two cases. Okay, so if the angle of projection is not equal to 0, like here in this case, that means that the initial velocity has both the x and the y component. Because remember that you can calculate for the x component of the initial velocity using this equation, and you can calculate for the y component of the initial velocity using this equation. So if you have values, non-zero values for the angle of projection, you will always have a non-zero value for this and this. So you can definitely, which means that you can definitely use the general kinematics equations for projectile motion as listed here. However, if the angle of projection is equal to 0, as shown in this case here, if the angle of projection is 0, so these are the cases where the projectile is not thrown upwards or downwards, but rather just thrown horizontally straight, like that one, directly horizontally. So here you can see in the equation that the y component of the initial velocity is equal to 0. This is because the sign of 0, if your angle of projection is equal to 0, the sign of 0 is actually equal to 0. So which means that your x component of the initial velocity will definitely be equal to 0. Okay? So So the y component of the initial velocity, which is equal to the magnitude of the initial velocity times the sine of the reference or of the angle of projection, is equal to 0. But on the other hand, the x component of the initial velocity, which is equal to the magnitude of the initial velocity times the cosine of the angle of projection, which is equal to 0, must be equal to the initial velocity. And the reason for that is that cosine of 0 is equal to 1. So if you multiply 1 by the magnitude of the initial velocity, that should be just be equal to the initial velocity. So if the angle of projection is equal to 0, that means that your initial velocity does not have y component, but rather your initial velocity will only be equal to the x component. So if the angle of projection is again 0, the initial velocity is just equal to the x component, and the y component of the initial velocity is equal to 0. So in this case, the kinematics equations for the x component of the projectile motion will be reduced. So in the following equation, so your x component kinematics equations will just be the same, only that now your initial velocity will only have the x component, and so your initial velocity is just equal to this and just equal to this, the final x component of the velocity. The initial x component of the velocity is just equal to the initial velocity itself. And since your y component of the initial velocity is 0, the y component equations will be affected, as you can see here. So this first equation will be reduced, so this one is equal to 0. So this will be reduced to just this one. So your final y velocity is just equal to the negative of the acceleration due to gravity, which is 9.8 meters per second squared times the time, while this second equation will be reduced as well because this is now equal to 0. So y minus y naught is just equal to 1/2 of the final y velocity times the time. Again here, this will be reduced, so we remove the term here. So you are left with the final y position is equal to initial y position minus 1/2 of g times square of t. And here also, this is also reduced, so this is equal to 0. So you have the final y velocity squared is just equal to the negative of 2 times the acceleration due to gravity times the vertical distance traveled. So take note that we have here positive 9.8 meters per second squared because we already incorporated here the negative sign. But if you put plus or the positive sign here, this will be negative 9.8 meters per second. So do not be confused by this. So what if the projectile has no initial velocity at all? So this is the case where the object, which is initially at rest at some higher position, is just released and it drops freely to the ground without any force applied to it other than the gravity. So in this case, both the x component and the y component of the initial velocity are 0. Hence, this is just a free fall motion. So we can therefore say that the free fall motion is just a projectile motion with no initial velocity. So in this situation, the kinematics equations for the x component are of no use. The first equation becomes completely 0, as you can see here, while the second equation just gives 0 horizontal distance traveled. So an object just dropped from higher position lands on the ground at exactly the same position along the x-axis, or its range will be equal to 0. And the y component kinematics equation in this case are just the same with the previous slides here, this one, wherein the y component of the initial velocity is just equal to 0. So therefore, for free fall motion, the kinematics equation applicable are only this reduced y component kinematics equations, wherein the acceleration is constant at negative 9.8 meters per second squared. So These equations are for projectile motion, but if you are dealing with free fall motion, that means that is just a projectile motion with no initial velocity. So for free fall motion, the equation, kinematics equation, will just be this set of equations. Okay, so now let's have an example. So a ball is thrown 100 meters above the ground at an angle of projection of 30 degrees and with an initial velocity of 8.5 meters per second. First question is, how long was the ball in the air? Or we are referring to the air time. And second, how far from the cliff will this ball land? Or in other words, it is asking for the range. So our strategy is to first determine which component of the motion relates to the unknown or what is asked in each of these problems or in each of these questions. So the amount of time that the projectile spends on the air only relates to the y component or the vertical component of the motion, whereas the range, on the other hand, depends on the horizontal velocity and the time it spends on the air. So first, let's recall the x and the y kinematics equations and the equations for the calculation of the x component and the y component of the initial velocity. So the first step is to calculate for the x and the y components of the initial velocity as shown here. So these are the equations. We have here the x component of the initial velocity just equal to the magnitude of the initial velocity, which is 8.5 meters per second according to the given of the problem, times the cosine of the angle of projection, which is 30 degrees. So 8.5 cosine times cosine of 30, that should give us 7.36 meters per second. So this is the x component of the initial velocity. For the y component of the initial velocity, all we have to do is to multiply the magnitude of the initial velocity, 8.5 meters per second, times the sine of the angle of projection, which is 30 degrees. So 8.5 times sine of 30, that should be 4.25 meters per second. So now we have the x component and the y component of the initial velocity. So then, since the air time depends only on the y component of the motion, we treat question number 1 as a one-dimensional vertical problem. So first, we will look at the kinematics equation that will solve what will solve the problem. So to start, equation number 1 is problematic since we do not know the final velocity of the ball. Equation number 2, in the same problem, we do not know the final velocity. The equation number 3, however, is fine because we know the final and the initial positions, the y and the y naught. We know the y component of the initial velocity based on this initial calculation. And we know the acceleration due to gravity, g is equal to negative 9.8 meters per second squared. So in equation number 3, the only unknown is the time. Hence, we can use this equation to solve for time. So first, we just rearrange the equation so that the initial position is in the right side. So this is the equation. We transpose one term, this initial position, to the other side. So we have this. And then we just rewrite the rest of the equation here. Before we proceed, we have to take note that we will consider the initial position of the projectile as in the origin all the time for simplicity. So we will assume that the initial position of the projectile, which is this point, is at the origin, which means that the initial position is at x equal to 0 and the initial y position is also at 0. And then after that, we plug in the values. So the final y position is at the ground, which is 100 meters below, so that should be negative 100 because again it is below the origin, right? So anything below this initial position must be taken as negative. So we have here negative y, and then our initial position is at the origin. We take it as y equal to 0, and then that should be equal to the initial velocity, which is the y component of the initial velocity, because we are using here the y component. So 4.25 meters per second times the time minus 1/2 of the acceleration due to gravity. This is already positive 9.8 meters per second squared because the negative sign is already indicated here or reflected here. And then we multiply it with the square of the time. So if we will try to tidy out this equation, this is just negative 100 is equal to 4.25 meters per second squared times the time minus 1/2 times the 9.8 meters per second squared times the square of t, or we can also rewrite it in terms of this. So we just equate it to 0. So we transpose all of the terms to the right so that we can equate it to 0. Okay, so that gives us an equation, quadratic equation with respect to time. So to solve for t, we will use the quadratic equation. We will first write this in the standard form such that the first term is the term of the square of t. And then the second term should be the term of the t, and then the last term is just the constant. So, and that should be all equal to 0. So to solve for t by quadratic equation, all we have to do, if you can still remember, is that if you have an equation in this form, a times x squared plus b times x plus c is just equal to 0. If you have an equation in this form, which is also the form of our equation as you can see here, we can always calculate for the x using this equation. So we can calculate for the x by just x is equal to negative b plus minus, so we have here two values, plus minus the square root of the square of b minus 4ac all over 2a. And so to use this equation, to solve for t, we will let x be our t, and then we let a be equal to negative 4.9, as you can see here. So this is our a, and b is equal to 4.25 because again the middle term b is equal to 4.25, and then c is equal to 100, which is the constant term. And then after that, we will now solve for t. We just plug in the values in this equation. So we have here negative of b, which is 4.25, plus minus square root of the square of b, which is 4.25 squared, and then minus 4 times the a, which is negative 4.9, times c, which is 100, and then all over 2 times the a, which is negative 4.9. So do not forget the negative sign here. So if you will evaluate this equation, so this will give us two terms. The first, two answers. So the first answer is obtained when this operation here is plus, and then the second value of t is when this operation here is minus. So you have two values of t. So we have the negative 4.10 and negative 4.97. And since the time can never be negative, we will just discard here the negative value. So which means that t is just equal to 4.97. So the ball therefore spent 4.97 seconds in the air before hitting the ground. Now, to solve for the range, which is the second question, or the horizontal distance traveled by this projectile, we will use now the kinematics equation for the x component, since again, the range is only dependent on the horizontal motion of the projectile. So we just rearrange this second equation here, remembering that the final x position minus the initial x position is equal to the range, and it is equal to the x component of the initial velocity times the time. So the air time uh, is just this answer here in the first question. So we have here from the calculations a while ago also, we have, as you can see here the x component of the initial velocity. So we have here v not x is equal to 7.36 meters per second. So therefore, the range, which is equal to the final x position minus the initial x position, is just equal to the x component of the initial velocity, which is 7.36 meters per second times the air time, which is 4.97 seconds. So that shall give us um, 36.6 meters. Hence, the projectile had traveled a distance of 36.6 meters along the x-axis upon hitting the ground. So, for the summary, vertically, the projectile is in constant acceleration in response to the Earth's gravitational pull, and horizontally, the projectile is in constant velocity, and so its horizontal acceleration is equal to 0, so it moves equal x distances in equal time intervals. And at the top of the trajectory, the projectile has 0 vertical velocity at the zenith, but its vertical acceleration is, of course, still negative g, which is the negative 9.8 meters per second squared. Also, remember the sign conventions illustrated here. So the initial position of the projectile is taken as in the origin, or at the x equal to 0 and y equal to 0 position for simplicity in the calculations. And all the vertical distances above the initial position are all positive y-axis values, while the values here below the initial position are all taken as negative y-axis values. The range is also measured from the initial x position, which is x equal to 0 towards the positive x-axis. Also, you have to memorize here the kinematics equations for the x component and the y component of the projectile motion.